Okay, hello. So far we have studied how to calculate probability from the standard normal distribution and how we can invert the standard normal distribution so that we can find the value that yields a certain probability. So like percentiles. So, okay, it was anyhow. We have to borrow the computer. We have the power of the computer to calculate that probabilities. But the problem is that we only learned how to do it for the standard normal distribution, which means we restricted the mean to be 0 and the variance to be 1. That means if your normal distribution had a different parameter, like if the mean was not 0 or if the variance was not 1, then the standard normal distribution cannot be applied. So we are going to study how we can handle this problem, like a normal distribution in general, like regardless of the parameter values. So we are going to use standardization to make a non-standard normal distribution into a standard normal distribution. Then so like so any normal distribution can be converted into a standard normal distribution using the process that I am going to introduce in this video. So what we are going to use for the standardization is the linear transformation results we learned in chapter 3 and 4. So remember that suppose that x is the original random variable, and say that the y is the transformation of the original random variable, but the transformation is linear. That means you only multiply something and add something. Excuse me. So as long as the original random variable is linearly transformed, then we know how the new random variables, the mean and variance are determined. Like we know that the mean of the new random variable follows the same linear transformation of the original mean, but the variance is affected by the multiplication, and especially in particular it's squared by it multiplied by the slopes squared. But the additive term has no effect on the variance. So the variance is a squared times the original variance. But the standard deviation, if you are interested in the standard deviation instead of the variance, then it would be more simpler. It would be simpler like this. So anyhow, we know how to manipulate the mean and the variance, which are the parameters for the normal distribution. So then let's think, and there is an additional mathematical result that's very useful. I'm not going to prove this, but we know that we have that if the original random variable was a normal distribution, then any linear transformation of the original random variable is also a normal distribution. So again, it may seem very obvious and like an automatic result, but actually not. So not many distributions have this property. For example, if you replace normal with like binary or binomial, this statement becomes false. It does not hold. So this is another very nice property of normal distribution. So anyhow, so if you combine these results, the results from the linear transformation of mean and variance, and if you know this, then what we can say here is if we know that the original random variable x follows a normal distribution with parameter mu and sigma squared. And then, if you take the linear transformation of x, then the resulting random variable would follow a normal distribution with these parameters. So the mean is a times mu plus b. So mu is the original parameter. It's linear transformed. And the variance parameter becomes a squared times sigma squared, where the sigma squared is the original variance. So in that way, like using the normal distribution and the linear transformation results, we can characterize the linear transformation of a normal distribution. So we are going to use this the other way. That is, what we hope to do here is, like here, we have a normal distribution random variable, and we would like to study this normal distribution. But it is not standard. We would like to make this normal distribution into a standard normal distribution. So what we are going to do here is, we would like to transform this normal distribution into y, but we hope to make this new random variable a standard normal distribution. So we would like to have the mean of the new random variable to be 0 and the variance of the new random variable to be 1, so that the new random variable is a standard normal distribution, right? This is how we standardize a normal distribution, even if it's not standard, right? And it is easy to find what values for A and B would satisfy these two result equalities. The answer is A must be 1 over sigma, so divided by standard deviation, and B must be minus mean divided by standard deviation. So that means if you multiply 1 over sigma and subtract mu over sigma, then the linear transformation can be written in this way in the end. So what you are doing here is, it makes sense. So x is the original random variable with parameters mu and sigma squared. What you are doing here is, you subtract the mean minus mu. This is to recenter the random variable around 0. So this makes the center of this random variable to 0. And then divide by sigma, standard deviation. That means if the variance is large, variance sigma was larger than 1, you have to make it more concentrated around 0. And if sigma was smaller than 1, then you have to make it wider, like more spread out. So these two parameters, as I said, we know that the normal distribution is defined by the location center, the central location, and the spread. So those two parameters can be handled, standardized in this way, which is a very natural and easy process to make a normal distribution into a standard normal distribution, right? And then, so as a result, we can say that it is Z. Remember, Z is a notation, common notation for standard normal distribution. So this is now the normal distribution. Transformation of X becomes a standard normal distribution. So we may utilize the information about the standard normal distribution. And Z it's not just a technical transformation, but it has meaning. This is how this is the standardized test score. For example, if X was a test score, Z could be understood as a standardized test score. So that means Z measures how many standard deviations X is above or below from its mean, right? So z measures the relative distance from the mean. That's how we can interpret this z. So if x increases, z would increase too. And if x is greater than mean, then z is positive. But if x is below its mean, and z is negative. So we learned this kind of interpretation in chapter 4. This is how we interpret the standard deviation. If you interpret the standard deviation as a unit of volatility, like a variability. So the standard deviation measures the distance from the mean, right? It's a unit. Okay. So, but anyhow, we are going to use this as a like a algebraic tool to calculate the probability, right? So then, for example, I will show you how we can use the standardization process to calculate the probability of non-standard normal distribution. Let's say you are interested in this probability, probability that x or normal distribution, possibly non-standard normal distribution x, smaller than or equal to a. So if you would like to calculate this probability, but if it is non-standard, we need to standardize x. So our goal is to make x into z, right? But so we have to subtract mean and divide by standard deviation. But what you have to remember here is the inequality must remain the same. To keep the inequality the same, you have to do the same manipulation on the other side of the inequality. That's a simple mathematical principle. So x smaller than a is replaced by this inequality, which is mathematically equivalent. X minus mu over sigma is smaller than a minus mu over sigma. So then, after this transformation, the left-hand side becomes a standard normal distribution, z. So we are going to rewrite, x minus mu over sigma as z, because this is a standard normal distribution now. On the other hand, a minus mu over sigma is a number you have to calculate, right? I'm going to show you examples how we handle this part, but in many cases, this is not much problem. Usually, you know what is a, and if you know the parameters, then you can calculate this part. So, and then in the end, after the transformation, the original probability we wanted to calculate becomes a probability about a standard normal distribution now. It is about standard normal distribution, and we know how to calculate the probability about the standard normal distribution. Like, we learned how to do it on Excel. So you may use that technique to calculate this probability, right? Now, we are going to consider an example like this. So think about this example. Suppose that I'm interested in the mileage of a tire, like say the life, how long a tire can endure in terms of mileage. And I'm going to assume that the tire's life, the longevity of tire can differ across tires, and its distribution is a normal distribution with these two parameters. So on average, the mean of tire mileage is 35,000 miles, but some tires may last more than others, so the variability, sigma, standard deviation, is 5,000 miles. So then clearly, it's not a standard normal distribution. Mean is not 0, sigma is not 1. So it's non-standard normal distribution. Okay, if you know that, and then we would like to calculate the probability that a, a tire is worn out before 40,000 miles. So we would like to calculate this probability. A tire cannot last 40,000 miles. Exactly, this is the same structure of as the example I gave you in the previous slide. So how can we calculate that? We know that this is non-standard normal distribution, so we would like to transform x into a standard normal distribution by this manipulation, this procedure, standardization. Standardize, subtract mean, divide by standard deviation on both sides. Remember, we have to when you standardize x, you have to standardize 40,000 miles at the same time to maintain the inequality identical, right? So then the random variable becomes z, and the right hand side is just a number. You can plug in the parameter values. So then it is easy to calculate. 40,000 miles, 35,000 miles divided by 5,000. That is 1. In the end, what you have to calculate is probability z minus 1. This is the same probability as a tire cannot endure 40,000 miles, right? In other words, you may interpret it this way. 40,000 mile is the mileage that's above the mean by 1 standard deviation, right? The mean is 35,000 and standard deviation is 5,000. So if a tire endures 40,000, that means the tire mileage is 1 standard deviation longer than the mean. So this is this number captures the relative distance from the mean, right? Anyhow, like you need to calculate this probability from Excel and use some function formula on Excel to calculate probability smaller than 1. Then you are going to get 84%. That is the probability that a tire cannot endure 40,000 miles. The probability we wanted, right? So simple 2 steps. As kind of mechanical process. Okay, I'm going to ask you this question. This is an exercise for you. Apply the same idea and use Excel or calculator to calculate this probability. Same thing, everything is same, but you need to calculate probability before 32,000 miles. I'm going to continue in the next video. So in between them, please do the algebra and choose your answer, and then watch the next video to see if you are correct. Okay, see you there. Bye.